So whether do you know what entropy is?
No.
Hold on a second. Entropy or S. So now entropy is like it's like a it's a very popular concept which has many different applications. And that is that entropy literally means it's the measure. Like if somebody is going to ask you about what entropy is, it's the measure of the disorder of a system. I mean, that's it. So it's you're measuring disorder, right? And S is that. S, the unit for S is joules per Kelvin per mole. I'm going to come to that. How do we get to that unit? And how do you measure disorder in a mathematical way? But initially, we're going to talk about it in qualitative terms, like uh, without any doing any mathematics. So, so I'm going to show you. So over here, I'm going to show you. I mean, there must be just a second entropy and so let's say there are marbles in a glass jar. If I can find an appropriate image, just a second. Here. So let's just take this image. So I've got two glass jars and they've got, let's say, marble balls in them. Which one do you think has more disorder? Or which one is the higher entropy one?
Is it the second one?
It's the second one. So remember now, whenever you hear the term entropy, it literally means disorder. So if I say something has very high entropy, that just means it's very disordered. If it's got a low entropy, that means it's highly ordered. So this one is low entropy, and this one over here is your high entropy state. When you move from low entropy to high entropy, that's basically a change in entropy, and change is represented by delta S. So if your disorder increases, that's delta S positive, right? So if you go from low entropy to high entropy or low disorder to high disorder, you're gaining disorder. So that is delta S positive. So that's a positive entropy change. And vice versa, if you're planning to go back from from a high entropy state all the way to a low entropy state, that is referred to as delta S negative, right? Is that clear?
Yeah.
So So let's say you've got, now apply this thing. If you've got you've got a very nice and tidy room, and it turns into a very messy room. So what is that? Delta is positive or negative?
Positive.
Okay, that's a gain of disorder, right? So anyway, so that's a simple concept of what delta S is. You can apply it to any place. Now, which state, low entropy or high entropy, which state do you think is more stable or is more likely to exist or is a higher probability? A high entropy state or a low entropy state?
High.
Okay, so this high entropy state is the more probable state, right? Having your marbles arranged in that way, that's got a lower probability. So this state, we're more interested in this state. This is the one, this is the stable state. This one has a higher probability to exist. And it's also referred to as your low energy state. So you've got a messy room and you've got a neat and tidy room. Which one is the most stable state? The messy.
The messy room.
And why do you think that's the most stable state? Like, why do you call it a stable state?
Because it's the highest probability and the lowest energy.
So so it's I mean you can think of it as a natural law, right? Because you see these two states, you intuitively know that the high entropy state, this is a state that's more likely to exist, and this is the one that's least likely to exist. So if you apply it to your room, it's harder to actually keep it clean, and it just turns messy on its own, right? You don't pretty much do anything, and it's just messy. You have to apply a lot of energy to actually make it neat and tidy, right? Is that clear?
Yep.
So but there's a mathematical justification for that as well. Like, why is your messy room the most stable state, right? Like, if you've got a messy room and you use that room for, let's say, 30 days, and after 30 days it's probably going to be still messy, right? So that means that's a stable state. The messy room kind of maintains its messiness, right? Whereas if you have a neat and tidy room, you use it for 30 days, after 30 days it's not going to be neat and tidy, it's going to be messy, right? So basically delta S being positive is easier. It's a lot easier. So you've got these marble balls, right? Now if you shake the marble jar, you're probably going to end up with the high entropy state. You're probably not going to be, no matter how much you shake it, the low entropy state has a very, very low probability. It's not going to, I mean, it's not going to maintain itself. It's not going to be stable, and it's very hard to achieve that state. Okay, so that's your high energy state. You have to like give it a lot of energy to actually achieve the low entropy state. That's a lot harder to actually achieve. And there's a reason for that. And the reason is, why is the messier state the more stable state? There's a reason for that. Probabilistically, like, how many different states, possible arrangements can you have for the marble balls to be arranged in a neat and tidy order, right? It's just a few states, right? Like, you've got, I mean, all these marble balls can exist in hundreds of thousands of different ways, right? They can be arranged or put together. Uh, there would just be a very few states that would, out of hundreds of thousands of different states, there would just be one or two states where you could actually arrange them in a neat and tidy order. Most of the time, most of the states that you're going to have are going to be are going to be the high entropy states. So they probably have a probability that's close to 1 or 100%. This state over here has a probability close to 0%. The same applies to your room. Like, if you want to keep your room neat and tidy, there's probably just a few ways you can actually put it in a neat and tidy arrangement, right? But if you want to mess up your room, there are thousands of different ways in which you can actually mess it up. So the number of states the number of messy states or the number of high entropy states, that's a lot. So which is why whenever you do something, you're probably going to end up with a high entropy state. Is that clear?
Yeah.
So everything goes from gains disorder. It likes to gain disorder. This is easy. And the same pretty much applies to chemical reactions as well, that things they like to gain disorder. And and everything around you, that this applies to everything around you. There are few things where delta S goes from high entropy state to low entropy state. There are few processes where this happens. Living organisms is one thing where uh, when they're searching for life, like in other planets, because life is not all carbon based. So when they're searching for life, life is basically defined as something that goes from high entropy state to low entropy state. It does the reverse. Like my body would actually take random things from the environment and put it in a neat and tidy order. And so that is what living organisms do. And what living organisms eventually do is they also build structures that are more low entropy states. We build houses. Houses are low entropy state. The moment we stop living, or the moment we sort of exit a place, everything goes back to high entropy state. So basically, living organisms, all sorts of, they try to maintain a low entropy state. As anyway, so moving on, let's apply this to chemistry now. Okay, so remember, delta S being positive is easier. Delta S being negative is naturally more difficult. So chemical reactions, how to predict delta S for a chemical reaction? Now, one thing is, number one, if you focus on the change of state, so if something changes from solid to liquid to gas, what do you think this is? Delta is positive or negative? Solid to liquid to gas.
Is it positive?
Okay, so this one is positive. This is a gain of disorder. And the reverse is negative. So this is gain of disorder, positive. Positive, you go back, that's negative. Now that's negative. And I'll show you the change of states. Let's click image just a second. So what do you now also tell me one thing? When something changes from solid to liquid, there's a gain of disorder, right? When something changes from liquid to gas, there's another gain of disorder. Which delta S is larger? Liquid to gas or solid to liquid?
Is it liquid to gas?
Okay, so just remember, gases have a very high entropy. Solids and liquids, they kind of have very, very similar entropy. Okay, just a second. So just remember this delta S is much larger. So gases tend to have very high entropy. And gases create a lot of disorder. Solids and liquids, they don't really, I mean, liquids create disorder. Solids create the least disorder, but gases create a lot of disorder. So first thing, that's in a chemical reaction. So if your moles of gas increase, that means delta S is positive. So you tend to focus on a lot of moles of gas if they're increasing or decreasing. And that's pretty much it. Solid to liquid to gas and moles of gas. Focus on the moles of gas. If states are the same, like if there is no change of state, then if just the moles, the number of particles increase, that's a gain of disorder. So then delta S tends to be positive. So then okay, let's say I've got water, gas, and it's turning into water liquid. What do you think is delta S? What's the sign of delta S?
Negative.
Okay, this one is negative. Okay, they're going to ask you a lot about this. So then you have calcium carbonate solid, and it decomposes. So it becomes a calcium oxide solid, plus gives off carbon dioxide gas. So what is delta S?
Positive.
Okay, that's a gain of disorder, that's positive. So if I have, let's say I've got 2SO3 and it decomposes and it forms 2SO2 plus O2, and they're all gases. So what's delta S in this case?
Positive.
Okay, there's a gain of disorder. Let's say I've got, do you remember addition polymerization?
Yeah, I think so.
Some other examples. So let's say there's addition polymerization happening and lots of alkenes just getting added up. So I've got alkenes. Let's say I've got lots of alkenes, and these alkenes, they join up and they form one polymer chain. What is this, negative or positive? Lots of monomers joining to form one polymer chain.
Is it negative?
Okay, so it's going to be negative because the number of particles are decreasing. So you have many monomers. And you've got one polymer chain out of them. So things are becoming more ordered in this case. What about, let's say, condensation polymers then? Now, in condensation polymers, what you have is that, as in condensation polymers, what you have is that you've got, let's say a polyester example. That what you have is you've got a molecule that's got that's a diol, and you've got a molecule that's a dicarboxylic acid. And then you have another molecule that's a diol, and so on. So the H and OH get removed, the OH and H got removed, and they ended up forming a large polymer. So C double bond O. So this is what has happened, and every time condensation happens, a small water molecule gets produced. Right in between the H and OH that get removed. Now, what do you think that is? Delta is positive or negative?
Is it positive?
Okay, this one is going to be positive because the number of particles are increasing because of the water molecules getting released. So in this case, the number of particles. So every time H2O gets produced, that's why. That's it. Delta is positive, delta is negative. So we're going to focus why that's important. One reason why it's important is that we know that delta is positive is easier to happen compared to delta is negative. Okay, but there are other applications, especially related to thermodynamics. You'll realize that delta S is way more important compared to delta H. The world actually, I mean, all the systems, thermodynamic systems, the one that rely on heat energy, etc., they work on entropy change, not an enthalpy change. For example, if you and let me give you the importance of this thing first. Okay, how do you think petrol produces or produces energy and makes the engine work? Do you have any idea how that happens? Like, how does petrol produce energy?
So isn't it when it burns and then that produces energy?
In what form does it produce energy? Like, is it heat energy, electrical
Is it
energy?
heat energy?
But remember when petrol burns, all that heat energy is kind of very pointless. It's not required. I mean, petrol would have been an excellent fuel if it hadn't actually produced any heat energy at all. So cars don't actually work on that. They don't need that heat. I mean, you've got radiators in the car, coolants in the car that are constantly removing that heat. They don't actually need that heat. So and the same applies to pretty much all the thermodynamic systems. The heat is actually kind of very, very pointless. So car engines work on delta S. They work on entropy change. Not really, although delta H is useful, but not really on the heat that's produced. Okay, so remember, we would refer to heat as delta H, the enthalpy change. Like if you burn a mass, right? You burn a match, heat is produced, right? That heat energy is kind of very, very pointless. It doesn't really do much. On the on this, but at the same time, if you burn a firecracker, right? There's not a lot of flame or heat produced, but that produces a lot of work. So I'll just give you an idea about why this is important. So what happens is car engines have these pistons in them. So there's a movable piston. So let's place. Sorry. So there's a movable piston, and here's an octane molecule, which is C8H18. That's your high octane fuel. Now, as soon as you burn it, what happens when you burn it? This octane molecule, it does produce a lot of heat energy, TK, and I told you that's kind of pointless. It's not really that important. What's more important is that when you burn this octane molecule, you get what? You get 8 carbon dioxides and you get 9 water molecules, right? So all of a sudden, in your car engine, in this small chamber, as soon as the octane lights up and burns or reacts with the oxygen inside it, it produces a lot of carbon dioxide, lots of tiny molecules. So all of a sudden, this tiny molecule, it explodes into tinier pieces, reacts with the oxygens, and produces 8 carbon dioxides and 9 water molecules. So there are lots of carbon dioxide and water molecules being produced, right? So what would they do? Is this delta S positive or delta S negative?
Positive.
Okay, that's positive. So when disorder gets created, work is produced because these particles, there's a lot of disorder, a lot of mess being created. These particles are going to go and strike the piston will start moving up. So the heat energy is not involved. I mean, petrol burns, catches fire, etc. That's kind of irrelevant. That's not important. What is important is that a lot of delta S gets produced. Burning petrol would have been useless if one molecule got converted into another molecule. That's it. So that would not have actually worked. That would have not have actually been able to move the piston. So the piston is basically moving up. Why? Because disorder gets created. And when is work produced? When delta S is positive. So most of the things around you, they actually work on delta S. They don't really work on delta H. Burning a match doesn't really do anything, but burning a firecracker, that produces a lot of disorder and it produces a lot of work. An explosion produces a lot of disorder, or in other words, it creates a lot of work. Is this clear? That why delta S is positive is important.
Yep.
Okay, so things don't really work on enthalpy change a lot. Okay, that's why delta S is important, because systems would actually, this will be important in chemical reactions, especially in thermodynamics, because we want delta S positive to be maximum positive. We want reactions where a lot of disorder gets created. That disorder can be used to run thermodynamic systems. How does a steam engine work? So, I mean, the steam engine pretty much has the same concept. Now, the steam engine reaction, that's actually endothermic, unlike the petrol combustion reaction, which is highly exothermic. The steam engine reaction, what happens in the steam engine? It's water liquid that turns into what? Water gas. Now, that reaction does not produce heat, it actually consumes heat. But as long as delta S is positive, so delta S is very positive in this case as well. And something similar happens, that the liquid water, when it turns into steam, there's a lot of energy, there's a lot of disorder, and that disorder helps in moving the piston. So the enthalpy change is irrelevant. In one case, it's exothermic. In the other case, it's highly endothermic. So that's kind of irrelevant. Delta S is what's important. ठीक है. तो अब ये करें कि we'll just practice finding out how to figure out whether delta S now qualitatively, no mathematics. ठीक है. So where's the entropy worksheet? Just a second. This is just the guesswork. So he's saying that why is the delta S for reaction 1 so positive? I mean, what's the explanation for that? Why do you think disorder is increasing?
The moles of gas is increasing.
I think that's it. That's a simple one-line answer. So the moles of gas, you had 1 mole of gas in the products, and you had no moles of gas in the reactant. That's it. So what's meant by the entropy of a system? That's the measure of disorder of a system. That's it. NaCl dissolving in water. What is that?
Positive.
Okay, that's positive, and why?
Because it's changing from solid to aqueous.
Okay, so it's solid where the particles are like tightly packed and how to arranged in a very orderly manner. Yeah, they have a regular arrangement, and then they turn into. They also dissociate. The number of particles increase, right? So the number of particles increase, and they turn aqueous as well. Aqueous state is kind of the same as liquid state. Water solidifying to ice.
Negative.
Yeah, that's negative because gas water, that's liquid to change of state, liquid to solid. So I had to let me just tell you one thing. Water entropy change. Let me just sketch one thing about entropy changes, specifically related to change of state. So here's your entropy, and here's the temperature. So you've got ice at minus 200 degree, at minus 200 degrees centigrade, and you've got okay, let's keep that in centigrade. I said you've got ice at minus 10 degrees centigrade. What do you think is the change in entropy between the two? There's one at minus 200, there's ice at minus 10. Is there a huge change in disorder between the two states?
No.
I mean, they're kind of the same. They're probably arranged in exactly the same order, right? So remember one thing that whenever temperature changes, there's so here's your 0 degree centigrade mark. So what happens is that your disorder barely changes up till the 0 degree centigrade mark. It's increasing, like the particles are becoming energetic, so they might get slightly disordered, but that's not going to be a huge difference. It's ice at minus 10 and ice at, like, if I give you 2 cups of ice, one is at minus 200, one is at minus 10, you won't be able to figure out the difference, right? So is that point clear, that temperature barely has any effect on the change in disorder? Is that clear?
Yep.
What happens at zero then? Is there a change in disorder at zero? At zero, what's going to happen? It's going to melt. And then, sorry. So at 0, at 0, it's going to melt, and all of a sudden there's going to be an increase in disorder, right? Because now it's going to be in liquid state, right? Is that clear?
Yep.
So just the idea that disorder does not gradually increase, but temperature, it kind of remains constant. Then there's a huge jump, especially when there's a change of state. So, and then water is 10 degrees centigrade, 20, 30, 40. Uh, Even at 80 degrees centigrade, liquid water is still liquid water, right? So there's not a major increase in disorder, right? Is that clear as well?
Yep.
So you see two glasses of water, one at 10 degrees centigrade, the other one at 90 degrees centigrade. By looking at them, you won't be able to figure out the difference. Just slightly more disordered at 90, slightly less disordered, but not a huge difference. And then what happens? Then there's a huge jump when the temperature reaches 100. So now you've got this huge, massive jump at 100 degrees centigrade. So all of a sudden, a lot of energy goes into changing the disorder of a system. And then, so now about gases, do you think that gases at, if there's a gas at, if there's steam at minus, not minus, if there's steam at 110 degrees centigrade and there is steam at 1000 degrees centigrade, do you think there's a huge difference between the disorder, or just a very slight difference in the disorder?
A huge difference.
So remember, in uh, gases don't really have the same disorder at temperature. Why? Because gases can expand and liquids don't expand. So liquid at 90, liquid at 10 kind of remains exactly the same. But gas at 10,000 degrees centigrade and gas at 110, it's going to be a huge difference. So after this, the line kind of goes, uh, it becomes a linear line. It kind of starts rising up, because if you heat, if you heat gas, its disorder continues to increase. So when you're storing stuff, right? If ice temperature increases, doesn't really, it's not that dangerous. But if you're storing liquids, if the liquid temperature increases, there's not much of a worry about that. But if you're storing gases and their temperature increases, then there's a huge chance of explosions, because then there would be a huge change in disorder for gases. Is that clear?
Yep.
So, Bas, I'll do some more questions. Just a couple of more questions on this. Just a second. Let's just do this one. A liquid water is cooled from 80 to 60. So, negative or positive?
Negative.
Okay, because they're losing kinetic energy, and so they're becoming more ordered. Calcium chloride added to water, that's solid calcium chloride, and it's soluble.
Positive.
Okay, that's positive. And you've got lattice energy. What was lattice energy? Gaseous ions turning into an ionic lattice, right?
Yep.
So that's delta is what?
Negative.
Okay, that's negative. So okay, let's continue tomorrow then, and we'll cover the mathematical part tomorrow then. Okay, it's a small topic. It's just a very small topic. Not that big of a topic with very simple concepts. Okay. So
Okay.
let's continue tomorrow then.
Okay. Thank you.
Okay, take care. Allah Hafiz.